Hi, I'm Kai. Now I'm going to do the question 1 of homework 10 for probability and stochastic processes. The question 1, we need to collect the definition and simple properties like the probability mass or density, mean, and autocorrelation function of some special stochastic processes. The first process is Poisson process. For this process, we can consider the number of points in the interval T2, T1, like the number of telephone calls or the number of buses in the interval. So the probability of the points is equal to k in the interval will be equal to e to the power of minus lambda times t1 minus t2 times lambda times t1 minus t2 to the power of k and divided by the factorial of k. Lambda is the average rate, and the mean of the process e of x of t is lambda times t, and the autocorrelation is lambda squared times t1 times t2 plus lambda times the minimum of t1 and t2. And the next process is Poisson increments. This process, the definition of this process is y of t is equal to x of t plus epsilon minus x of t divided by epsilon. X of t is Poisson process, and epsilon is greater than 0 is a constant. So the probability mass function p of y of t is equal to e to the power of minus lambda times epsilon times lambda times epsilon to the power of n divided by the factorial of n. And the mean of this process, e of y of t, is equal to lambda. And the autocorrelation is lambda squared when t1 minus t2, the absolute value, is greater than or equal to epsilon, and lambda squared plus lambda over epsilon minus lambda times the absolute value of t1 minus t2 divided by epsilon squared when t1 minus t2, the absolute value is less than epsilon. And the next process is Poisson impulses. The Poisson impulses is defined by the derivative of Poisson process with respect to t. So the z of t is equal to the derivative of x of t, and it is also equal to the limit of the Poisson increments process when the epsilon goes to 0. So the mean of this process, e of z of t, is lambda, and the autocorrelation is lambda squared plus lambda times delta of T1 minus T2. The next process are semi-random telegraph signal. So in this process, we also think about the number of points in the interval 0t, and the probability of getting k points in this interval is p of k is equal to e to the power of minus lambda times t times lambda t to the power of k divided by the factorial of k. Lambda is density. So xt will be 1 when k is even, and x of t will be -1 when k is odd. So and if x of 0 is a fixed one, then we call it a semi-random telegraph signal. The mean of the semi-random telegraph signal E of x of t is e to the power of -2 times lambda t, and the autocorrelation is e to the power of -2 times lambda times the absolute value of T1 minus T2. And the next process is random telegraph signal. So we define the random telegraph signal as y of t is equal to a times x of t, and x of t is a telegraph signal and a is a random variable and independent of x of t, and the probability that getting 1 and -1 is equal 1/2. The mean of random telegraph signal is e of x. E is 0, and autocorrelation is e to the power of -2 times lambda times the absolute value of T1 minus T2. The next process is random walk. So we toss a fair coin infinite times. If the outcome is head, we take a step forward, and we denote it by plus x. If the outcome is tail, we take a step backward, and we denote it by minus x. So each step moves plus x or minus x with equal probability. So if we toss the coin n times, we can define the random walk by x of nt is equal to k times x minus n minus k times x, and it is equal to 2 times k minus n times x. K is the number of head, so n minus k is the number of tail. So the probability mass is a binomial distribution, and the probability of head and the probability of tail is equal, is 1/2. And the mean of the random walk process E of x of nt is 0, and the autocorrelation R is the minimum of n and m times x squared. And the next process is Wiener process. Wiener process is a limiting process of random walk. So we can define Wiener process as the limit of x of t, and the step s goes to 0 and t goes to 0 and n goes to infinity, and it is equal to the limit of x of t. T goes to 0, n goes to infinity, x squared divided by t goes to alpha. And x of t is a random walk process, and alpha is a constant. So the density function of Wiener process is a normal density function. F w of w and t is equal to 1 divided by the square root of 2 times pi times alpha times t times e to the power of w squared divided by 2 times alpha times t. The mean of Wiener process is E of w of t is 0, and the autocorrelation of this process is the minimum of t1 and t2 times alpha.